Okay, let's get to the bottom of this about law of sines. Now, you've been learning about law of sines. You've been learning about law of cosines. Something weird that happens with law of sines that does not happen with law of cosines is that law of sines can give weird answers. This comes in two basic flavors, but the reason behind each of them is really the same. First of all, I'm going to take a look at this triangle that I've got here already displayed. What I did was I made the angles ahead of time. You can check for yourself. They do add up to 180 degrees. And then I fixed this length right here, the 15. I said, I'm going to make this 15. And then I used law of sines to solve for the other sides. But what I'm going to do is that even though I promise that these will actually work, I'm going to show that if I pretend that I don't know a certain angle here, specifically, if I don't know this angle, angle B, I'm going to pretend I don't know it. Law of sines is going to tell me that it's actually something different than what it is. It's going to be strange, but we're going to look at why that happens. It'll help to clear up any questions that you might have. So what I'm going to do is pretend that I don't know that this is 101 degrees. So I'm going to leave the number up there, but I'm going to just say, pretend we don't know this. Now, if we pretend we don't know it, it means that it's something that we have got to solve for. And I'm going to also say, pretend that we don't know, say, this angle either. Because if we knew two angles, then we'd be able to just add them up and subtract to get the, subtract from 180 to get the third angle. So I'm going to say that that sort of solution here is going to be off limits. So what I've got here is the three sides of the triangle plus one angle. Now, I could use law of cosines here to solve this. And in fact, that will give you reliable answers. But what's going to happen here is that if I try to use law of sines to solve for this angle in particular, angle B, something strange is going to happen. We're going to look at what, and then we're going to look at why. All right, law of sines tells me in this case, I've got an unknown angle. Remember, I'm thinking of the 101 degree angle as like our little secret. So, it's not really there, even though we know it's there. I'll say that sine of B over 15 is going to be equal to, and then the only other pair of things where I know both of them is going to be the 9.20 and the 37 degrees. So when you do law of sines, you can pick like a bunch of different pairings. I'm going to pick that one to compare this to because that's the other one where I know both of them. So I'm going to say that this is sine of 37 degrees over 9.20. Okay, well, so far so good. I'm going to say that that means sine of B equals 15 sine of 37 degrees over 9.20. And now I'm going to use my handy dandy Mr. Brain calculator person to get what this is going to be. Now keep in mind, we already know that it's supposed to be 101 degrees, but I'm going to get something really wacky here. Inverse sine of 15 sine 37 divided by 9.2. Make sure you are in degrees mode. Now, what I get here is just so strange. I didn't make any mistakes with putting it into my calculator. I put in all the right keys. I closed all the parentheses, stuff like that. So the measure of angle B, according to this, is going to be 78.89 degrees. That seems like it should not happen, right? So why would that happen when we fix the triangle ahead of time? Well, here's what's going to happen. First of all, the reason that this is detectable as an error, like something that's not reflective of the real triangle, doesn't just have to do with knowing it ahead of time. Because let's say that we did that we did try to get it with the 78.89 degrees. So, okay, let's say we don't know that something bad is going to happen. And we'll do, so we'll put the 78.89 degrees here when we know that it's really 101 degrees. Some of you might see what's coming already, but keep it under your hat. Now I'll use that to determine other stuff that I know. So I'll say, okay, well, 15 over sine of 78.89 degrees is going to be equal to 10.22 over the other unknown angle, sine of A. I can rearrange this to get A is equal to the inverse sine of 10.22 sine of 78.89, fit in there, divided by 15. That's 10.22. So let's see, what does A end up being now? If we played our cards right, this will show why that initial value is actually a problem. Sine of 78.89 and then divide by 15 on the inside. Okay. So I've got, this is not surprising. I knew ahead of time that A was supposed to be the 42 degrees. This is like 41.95, 41.96 if I round. So, okay, well, big deal. It's right. But hang on. The 101 degrees was what we needed in order to get 180 for the triangle. So check it out. We've got 42. Let's just call it 42. I know it's 41.96, but 42 plus 37 plus 70, and I'm going to call that 79. That's not 180. So what happened? Here's what happened. Here's what happened. Let me get rid of some stuff so I've got some room to write. The thing that happened is that sine, when you use the inverse sine function on your calculator, it assumes that you are in, you thought you were done with the unit circle? You're never done with the unit circle. Your calculator assumes that you are somewhere in this portion of the unit circle. So it gives you answers that assume that you're either in quadrant 4 or quadrant 1, because that's where sine is -1 down here and sine is +1 up here. So this interval from -π/2 to π/2, or -90 degrees to 90 degrees, that's where sine traces out all of its possible values. But we actually want angle B to be outside of this boundary. We want it to be at 101 degrees. But watch this. If I take the 70, let's call it 79 degrees right there, and then I draw 101 degrees right there, don't these two have the same sign? Heads going like this? Yes, because sine is the vertical. So what you can detect here is that if you find all of the angles of the triangle and it turns out that they don't add up to 180 degrees, the thing that went wrong was not your mistake. It was that one of those angles needs to be converted to a larger version of it by reflecting it over the y-axis. Here's how you could detect that this is going to happen. Let's see. I know that if the 42-degree angle is converted to the corresponding version, so 42 converted to the corresponding version over here, that would be 180 minus 42, that would be 138 degrees. Well, if this is 138 degrees, then that means 138 plus 37 leaves only 5 degrees for this. Now, this clearly doesn't make any sense because the 5-degree angle would need to be opposite the smallest side of the triangle. like a tiny, that 5-degree angle is really, really small. So 5 degrees would need to be opposite from the smallest side, but it's actually opposite from the largest side. It's opposite from the 15. So here's how you can tell that something's gone wrong. If the angles don't add up to 180 degrees, go back and interrogate the angles that you found using inverse sine. Every time you use inverse sine, you should say, does this answer make sense in the context of the actual triangle? There's one more way, just in case you're not completely out of patience yet, one more way that law of sines can give weird answers. And it has to do with when you have side angle data in triangles. Yes, side angle, not angle side. Grow up. So imagine that you have this triangle, which has a 30-degree angle here, a side that's 10 here, and a side that is 6 right here. And what I'm going to do is solve for this here angle using law of sines. It's the only thing I can solve for because I know this pairing and I know half of this pairing. So what I can do, if I give these names, I'll give this A, B, and C, making this side B. So I'm going to say sine of A over 10 equals sine of 30 over 6. Okay, so A will be equal to the inverse sine of 10 times sine 30 over 6. Yeah, I could reduce the fractions, but I'm about to throw everything in a calculator anyway, so why bother? Inverse sine of 10 sine 30 divided by 6 is 56.44 degrees. I'll just call it 56 degrees. Well, so far so good, right? However, you need to keep in mind that in this particular instance, like I said up here, this is side angle data for a triangle. Side angle, you might remember from geometry, is not a congruence postulate. So if you know side angle style information about a triangle, that doesn't tell you what the triangle is going to be. There are multiple possibilities. And we're going to appeal to the same sort of unit circle style argument in order to see that. A 56-degree angle looks a little bit like this. Well, guess what we're going to do with that to get the alternate solution? We're going to reflect it over the y-axis. These two have the same sign. And here we have a 56-degree angle. And here we also have a 56-degree angle. That's why they have the same sign. But then what is this angle in the yellow? Well, it's 180 minus 56. Minus 50 is 130, minus another 6 is 124 degrees. That kind of looks like the solution that I've got up here. This looks like it's probably the 124-degree angle that I've got depicted here. The other solution is going to be if the 6 is this way. So this angle right here, this is going to be the 56-degree angle solution. So it's important to know that this triangle has not one, but two solutions. And this is not breaking the rules of math. You learned way back in geometry last year that side angle is not enough to solve the triangle. So hopefully if you were paying attention last year, you do remember this and you can be like, oh yeah, that's cool. So now we know how to deal with side angle. Law of sines can give weird answers based on reflecting over the y-axis, which is why when you're finding unknown angles using inverse sine, you just need to be a little bit more careful.